All right. Hello, everyone. I was just catching up on some reading. It is a classic, Harry Potter and the Goblet of Fire. It is, after all, Harry Potter Book Day. But you know, I should actually be flipping through this book, Housing 2.0, a Disruption Survival Guide. I mean, after all, that's why you're here, and we are glad you chose to join us. You know, this is the first of 4 virtual seminars that will examine how to consistently optimize 5 key housing user experiences. This series is going to look and feel a little different than previous iterations. We're going to focus on performance and specifically on enclosures. And as a bonus, we're going to be joined by Ken Nelson of Panasonic for a presentation, discussion, and Q&A on IAQ. That's a lot of letters there. You know, my name is Mike Calignan, and I'm the Housing 2.0 Program Manager. If at any point you have any questions, please don't hesitate to reach out to me via the chat box or by email, and I'm going to put that address in the chat box in just a little while. Since it is Harry Potter Book Day, I guess that would make Sam the Dumbledore of Housing 2.0. He's formerly the Chief Architect of DOE's Building Technologies Office, but now is focused on creating and teaching the content for the Housing 2.0 program. That content is based largely on Sam's book, Housing 2.0, a Disruption Survival Guide. The full program was established to help empower you, our building professionals, to design and construct higher performance, healthier, more sustainable homes at a fraction of the cost. You know, Sam's going to lead us through today's seminar and also address your questions at the end. Now, before we get started, we have some magical sponsors I need to mention. The first is Schneider Electric, who is driving the digital transformation of modern homes with smart and sustainable energy solutions for ultimate comfort and energy efficiency. Their connected home ecosystem of smart energy management solutions provides digital control of energy use throughout a home, from the grid via their smart electrical panel to their connected wiring devices. Next, we have Jinko Solar. They are a leading PV module manufacturer and energy storage system integrator. The company has deployed more than 100 gigawatts of their Eagle modules in 160 countries globally, including more than 17 gigawatts right here in the United States. Eagle Storage brings together the best energy storage technology for turnkey hardware and energy storage services. We also have Panasonic Healthy Indoor Living Solutions, because they're helping builders across the country differentiate themselves with powerful, code-compliant, and cost-effective indoor air quality solutions that provide a safer environment for homebuyers. And as I mentioned before, Ken Nelson from Panasonic is going to be joining us. Finally, we have our newest sponsor, which is LV HVAC. As a leading proponent of the electrification movement, LG is proud to pave the way with arguably the broadest portfolio of home electrification products. From air-to-air and air-to-water heat pumps for HVAC, water heaters, clothes dryers, and washer-dryer combos, to advanced energy storage systems, EV chargers, and super efficient appliances, including the industry's first ENERGYSTAR certified induction cooktop, LG's innovation and technology will help us promote decarbonization and collectively create a better life for all. Now, during the course of today's presentation, you can submit questions for Sam or Ken. Simply use the questions box inside the GoToWebinar control panel. I'm going to review those questions and pose those to Sam or Ken after our presentation today. All right, I don't see a broom, but it looks like Sam is ready to take off on this educational journey.
Hey, thank you so much, Mike. And like Mike, incredibly grateful for our great sponsors. The program is incredibly grateful for their support. Again, Panasonic, Schneider Electric, Jinko Solar, LG Air Conditioning Technologies are carefully curated because they align with our mission to deliver better homes for lower cost. So let's jump into today's seminar. We're going to talk about today, session 1, Performance Matters. This is one of 4 sessions that I'll lay out for you a little bit into the presentation that comprises series 2, the last series for 2024 of Housing 2.0 seminars. So the outline for today, we'll start with a brief introduction of the Housing 2.0 program, why, what, how, that is the source of the content for today. And then pulled from the large content database from Housing 2.0, we're going to talk about performance and why it matters and why it's so critical. There are key changes that are absolutely just major forces acting on the industry. There's then the change in form performance that we need to address in new housing. And then relative to the overall performance, we're going to zero in on one of the most key parts of performance, the enclosure, and how to get that right. And then finally, how to optimize the enclosure for lower cost. Then we'll go into Ken's discussion about indoor air quality and open up for discussion. So first module today, why, what, how for Housing 2.0. The big aha data point that drives a lot of why I do what I do is a study by Lawrence Berkeley National Lab looking at where people spend their time every day, at work, at home, other indoor environments, dining, outdoors, cars. And what's a stunning realization from the data that was done in 2001 is that almost 70% of our time is in our homes. And when you look at the statistics after COVID, with all the kind of the embedded work at home transition, probably we're 75% in our homes every day. So it leads us to this kind of amazing concept, home is where life happens. And any of us in the housing industry, whatever role we serve, should feel inspired by what we do is create the life where people kind of spend their time. And the goal for why I do what I do, why I think many of you listening do what you do, is we're about making homes where life happens better. And the key thing about Housing 2.0 is I've expanded the scope of where I spend my attention to go beyond just performance, because I was just virtually just dominated by that, trying to get housing, ENERGY STAR certified home and zero energy ready home to market. And I had this realization that that is really just one leg of a five-legged stool. It's an absolutely must-have leg of the stool, but for consistently delivering, to be consistent delivering a better user experience at lower cost, there are four other experiences that also have to be addressed. The community experience, the design experience, quality, sales, and service, all those deliver a complete and expected user experience by every home buyer. And so performance is a must-have, but so are the other four. And there's a process for how I address every one of these five experiences. It basically is always the same. We have two business models. We have the older first cost driven business model and the housing and the Housing 2.0 business model. If we look at cost per home, the amount of money in step one, first investing in the user experience through experts and special features, we want to bump up with Housing 2.0, make extra investments where we know we have a sure thing, a user experience that will, if not transform, completely enhance how life lives in that home. And the second step is absolutely critical. The big, unique guidance, I think, from Housing 2.0 is that we then tie a whole comprehensive set of best practices for optimizing the cost, not just the construction costs, the ownership costs, wellness costs, and future value. And when we optimize all those, we have the net cost savings and added value that accrues. And the last step of Housing 2.0 is to translate that value. If the consumer doesn't see it and it's hidden, then it doesn't manifest when we go to market. So what we're finding through my analysis and observations of really successful builders who apply a lot of these best practices is there's an opportunity for 30 to 70% added value and cost savings compared to the existing business model. And that's basically the essence of Housing 2.0. What I love is at the end, when we do full day workshops and training programs, we do have a chance to really dive into success stories. Here's one, Walsh Construction in Portland, Oregon. They built the first building and then they said we can do better. And they just went into a comprehensive optimization approach for design. And just one of the five experiences optimized reduced the cost of construction almost 25%. And that doesn't account for all the added value that also comes from better spaces and better floor plans and better storage, et cetera. So this is really compelling to me. We have to do better is where the industry is going. And so the key resource I'm going to suggest to you is the book that Mike showed you at the beginning, Housing 2.0, Disruption Survival Guide. You can just run your camera over this um, code and get to our website. But this is where you get so much more detail than we can ever cover in these seminars. So let's move right in with the first topic, key changes impacting performance. I think if you got 100 housing professionals in a room and asked them to write a definition of high performance homes, you get 100 different definitions. And so I want to try to create some thoughtful logic about how we think about performance. And the best way to do that is by looking at these key changes. There are 4 of them. First is that there's housing disruption looming ahead. Many of you know who've seen my presentations, I do an hour to hour and a half just on all the research and data points around what's happening to the industry that suggest this disruption. I'll compress that into just a couple of slides. And then the next key change impacting performance is that zero energies and zero carbon have left the station. We'll talk about that. But along for the ride comes, with all these better homes, comes greater risks. And we have to manage those risks. And that's a key change that has to be recognized. And then there are all these hard trends that are absolutely pivotal in having housing that stands the test of time. So these are 4 key changes, and we'll look at them one at a time. So let's start with housing disruption looming ahead. Again, this is compressing a long presentation just to a couple slides to give you a sense of how important I know is where the puck is going. The old Wayne Gretzky quote about why he was successful. He didn't skate to where the puck is, he skates to where it's going. And I'll suggest we know where it's going by first looking at the problem. There are 4 crises driving substantial pain to the housing industry. One is user experience readiness. Home buyers are massively more informed. They have massively greater expectations. We have peer reviews and all sorts of other ways of differentiating builders. We have to be ready for this new world. Second is affordability. Housing affordability is off the charts. I think the current median price to median income ratio is 5.6 when 3 is considered affordable and 5 is like, it's insanely unaffordable. So we are, what we all know this is affordability is just crushing the industry. Then third is trades and the lack of trades. Their average construction age is 42 and a half. For every 5 workers that retire out of the industry, there are only 2 in the pipeline to replace them. There are some recent moves to get some little gains from that, but not nearly enough to meet the needs for 723,000 new workers a year. And finally is productivity. We are the only industry that's declining in productivity, and that's unacceptable when we have just such a millions of home backlog that have to be met to provide housing for Americans. So these are real substantial crisis points. And then we have solutions, though, that relieve the pain. In fact, there are 4 solutions. One is a user optimization approach, like I said, that extracts all the savings and value to create better homes for lower cost, kind of why you're at this workshop. And then there's mass customization. You know, I get beaten up a lot by builders every time I present recommendations in this mass customization space, but essentially we have to start realizing we can't afford to build all these custom tailored homes the way we do. There's just far too much customization, and mass customization can deliver the same or better products at lower cost. And then third, we can't be the only industry that's not digitized. Every other industry makes a virtual twin of a product before it builds it. We have to be fully digitized to, again, leverage all these additional cost savings from both avoiding problems and building more efficiently with digital virtual twin. And finally, systems built. You know, the idea of just building the field the way we've been building for hundreds of years is not affordable anymore. So systems built's critical. So when you put all this together, if we apply these solutions, we have a disruption, better homes for lower cost. And the way it lays out is here's the problem, these 4 crises. user experience readiness, affordability, productivity, trades, and then we have the disruption, the 4 solutions, market ready to relieve the pain. Just connect the dots. User experience optimization will provide homes that will meet and exceed expectations of buyers, and because they leverage and extract all these savings and add all this extra value, they're more affordable. Mass customization will take those user experience optimization solutions and create mass customized solutions with various building blocks that can be just easily assembled to create these great experiences at lower cost. A virtual twin with digitization will virtually digitize these solutions so they're even more market ready and more affordable and more productive. And finally, systems built is the only path to really mitigating this kind of cliff looming ahead where the workforce shortage will kind of crush the industry. So my view to the future is simply logically looking at what has to happen for the industry, and anything we do to make high performance solutions has to recognize this future. Okay, the second change happening is zeros left the station. And let's just look at the numbers. Just in terms of HERS ratings, there were nearly 4 million homes rated in 2023. I suspect we're getting closer to 4 million in 2024. Last year, I mean, the cumulative is 3.6 million. Last year, over 360,000 homes were rated with an average HERS index of 57. Probably a good zero energy ready home, you're really in the 40 to 50 range. So just the average HERS index for over 360,000 homes is already approaching zero ready kind of index. And the code index is 70 to 80 for the latest IRCC codes. Then we can look at the national codes themselves and how rapidly they're increasing rigor. This is just a curve that shows the energy use index with 1995 pegged to 100 and how the rigor has increased with reduced energy use requirements with each next iteration of the energy code. And what you should notice is that we've dropped about 40 to 50% since 2006. And effectively, that's a zero ready enclosure. And a good indication that's the case is the Zero Energy Ready Home program from DOE is pegged to 2021 IECC, I think starting next year, currently 2015 IECC. So these codes are already a great foundational baseline for the enclosure of a zero energy ready home. And then we can look at the states that are adopting these codes. This is a map that shows in kind of a tan color all the states that are targeting a zero energy code specifically. In green, the states that are targeting these more advanced codes that represent a zero ready home enclosure. And 2021 IECC is required for all HUD and USDA loans starting next year, which will further push almost all states to start using the 2021 IECC to get the far greater financing mortgage rates with the HUD code and USDA loans. So, and HUD is FHA. So again, these are just forces that are just going to keep driving to these latest zero energy ready codes. And then there's the voluntary certifications. ENERGYSTAR has marched past 2.5 million. Zero and zero ready certifications are also growing exponentially. I'll mention that the Zero Energy Ready Home program this year certified 8,000 homes, which is as many homes as are certified the prior 10 years, just this year. Next year, they'll be in the tens of thousands of homes because we'll talk about Beazer and Clayton Homes are going all in at 100%. Just those two companies are about 50,000 homes, 55,000 homes a year. So zero energy certifications is just off to the races. And then there's a driving force for moving there, the 45L tax credit, which locks in for 10 years, very significant builder rebates, $2,500 for ENERGYSTAR, $5,000 for zero ready, for single family homes, multifamilies, $500 and $1,000 respectively. And manufactured homes are $2,500 for ENERGYSTAR, $5,000 for zero ready. And again, this is what's driving so much growth so quickly. And so you see a company like Beazer going all in 100% starting next year, zero energy ready homes. And then I mentioned Clayton's going 100%, already starting the process substantially through their plants. And what's really stunning is that they're building zero energy ready homes, $148 a square foot, compared to numbers we see like 150 a square foot for minimum code homes. So it's just everywhere you look, the data is telling you this is a future, zero energy and zero carbon. And what's great is you have all these certification solutions for how you get there. There's a path for how every one of us can get to zero. High performance certifications, ENERGYSTAR Zero, Zero ENERGYSTAR, Air Plus, Water Sense, Fortified for Resilience, Green Building Standards, Zero Ready is with the Zero Energy Ready Home program and the Passive House program, Zero Net Energy with Passive House, and Living Building Challenge has a Zero Energy certification. All electric zero energy homes are coming on the market, and so are zero carbon certifications. So lots of ways to kind of figure where you want to be and how you move along the path, but it's a great way to prepare. And then we have the third item, which are all the greater risks imposed as we build much more high performance enclosures with these zero energy programs and better codes. And the reason risks go up is because of the major change in thermal and airflow through the assemblies. In low performance enclosures, you have much more thermal and airflow. High performance enclosures, much less thermal and airflow. And what drives risk is that you have a much colder surface on the cold side of the assembly, inside the sheathing or the drywall, depending if it's a warm or cold climate. And that creates, first of all, moisture risk, because when you have colder surface and less thermal flow to drive it, there's more wetting potential, and there's and less drying potential. And that's kind of a formula for lots of risk if any moisture can get in the assembly. There's like no room for error. So moisture risk is greater. And then comfort risk is greater because we have ultra low loads with such improved enclosures. And so we have less airflow through the duct systems. We have shorter cycles to remove moisture in the cooling season. We have longer swing seasons where we still have latent load on the front and back end, but no sensible cooling operating to create the dehumidification. And we have a market where dehumidification is like extra credit and has to start moving to becoming more mandatory in climates that get humidity. And the third risk is health. We have much tighter enclosures, so we have much more accumulation of contaminants that have to be managed. So all these risks are there, and it's not, oh my God, the sky's falling. It's that you manage the risk. We can do this. And the last force acting in this industry, these key changes, is hard trends that you can't ignore. This is the future with certainty. Disaster risk every day would just almost never disappear from the news. The magnitude and frequency of just insanely more devastating disasters is just growing and growing. Water shortages are a byproduct of a lot of the climate trends to much hotter temperatures and less rainfall in large regions of the country. We have to be dealing with water conservation. It's no longer extra credit in such a large portion of the country. And then we know we're going to this all electric transition. And we need to build our homes and enclosures and integrate in performance solutions that will be ready for this transition. So let's look at change in form performance. If all these key changes are acting on the industry, what is the imperative for us in building high performance? And the first set of building blocks is step one, optimize energy efficient performance. And we do that first with the enclosure. That is the most important part of the building. We have to get the enclosure right. And more we'll be integrating smart features in the enclosures, sensors and cameras, so we can better manage, again, things that might be happening, like if the enclosure is getting wet, if there's airflow or other issues with temperatures that are not where they should be. So a lot of things will be happening for efficient and smart enclosures. And the same with the equipment, efficient and smarter. So now we have a much greater enclosure. We can size the equipment and put in the equipment that knows what to do with a more efficient enclosure. And then all the rest of the components, the lighting, the appliances, all those should be efficient and smart as well. So step one, the next building blocks are managing those risks we just talked about: moisture, comfort, and accumulating contaminants. So we have moisture protection, insured comfort solutions for low load homes, and comprehensive indoor air quality. And finally, we have step three. We get ready for the future. If we know where the puck is going, let's get there. And we know disaster resilience is just pounding the industry. Insurance costs, property values, there's so many forces that have to be managed to protect homes for the future. Same in regions that are just locked in for ever increasing water availability issues. We have to integrate water efficient solutions. Again, this all electric transition, we need to have solutions that we can quickly transition all electric, or even start building all electric solutions today. And so this leads me to a definition of high performance. When I go and research definitions, I just can't find any that work for me to the degree I can find any really consistent definition in the industry. So I'm going to volunteer one that builds on this understanding and this set of building blocks: high performance, residence constructed with smart enclosure assemblies, systems, and components that ensure efficiency, durability, comfort, health, resilience, water conservation, and electric readiness. It's a mouthful, but any one of those left out is a huge impact on the home performance. And I'll give you a little definition just to amplify the definition. It's great to have a beautiful home, but it's just as critical to have a high performance home that lives, lasts, and works better. So when I go and move into Housing 2.0 and say, here's a framework for how we deliver better homes for lower cost, all these building blocks inform a very carefully curated set of strategies and actions you can take. And so first thing's the why. Why do we do high performance? Because protection matters. Protection from high bills, discomfort, inconvenience, poor health, lack of water, high maintenance, safety, and lack of sustainability. And what we do first is we optimize the enclosure. I mentioned that is the biggest, most substantial part of the home we build. We have to get it right. We do that with building science. And then there are a whole array of best practices for doing building science right. Then we have to get the operation right. You know, the whole way the equipment, the comfort, the water heating work, and they have to be efficient and smart. Then we have to optimize health. And we do that with comprehensive indoor air quality. Then we have to optimize water with water efficient solutions relevant to the location. Then optimize resistance with disaster ready solutions relevant to the prevailing risk. And finally, we want to optimize zero. And to do that, we have to be electric ready. And what we're doing today is I'm going to focus on the enclosure the rest of the way. And then I got Ken coming in from Panasonic to help out on the health side, talk about indoor air quality and ventilation, how we start managing contaminants from accumulating in our homes. So this is session one of the Better Homes for Lower Cost. Then on October 20, today's the 17th, so on the 24th, we have Better Homes for Lower Cost session 2, Comfort Matters. And again, I'm going to extract tens of thousands of cost advantage by optimizing comfort, and I'm going to bring in experts from LG air conditioning to talk about innovation for low load homes and comfort. So we'll do that next week on the 21st, on the 28th, I think. We have session 3 of the Better Homes for Lower Cost, Future Ready Matters, and we'll dive into all these opportunities to address being ready for water, disaster, electric, and things that really deliver a better user experience. And then we have a very special sponsor, Schneider Electric, which has these amazing solutions for really getting ready for the all electric future, integrating with solar, electric cars, all the things that are happening. So we'll do that in the 3rd week. And finally, November 7th, I believe, the Better Homes for Lower Cost session 4. The last one will focus on how you live matters. And here, that's not enough just to have a great performing home. We have to optimize design and community. And we'll talk about a lot of the highlights about ways you can extract hundreds of thousands of dollars of cost advantage and savings and value by applying those best practices. So that's how these 4 modules lay out. And so moving into the optimizing the enclosure, we have these, the strategy is building science under the set of strategies I showed you for optimizing performance. And the best practices, the top tier ones are bulk moisture control, airflow control, thermal control, and vapor control. And that's kind of priority order. You have to keep water out of these incredibly higher risk assemblies. That's just mandatory. You have to be really rigorous about keeping bulk moisture out. Then airflow, then thermal flow, then vapor flow. And then you have a whole series of more granular best practices for how we do that. How we have a whole set of tools for managing bulk moisture at the roof, walls, openings, foundation and site. Airflow is a combination of air barriers, air sealing and flashing details. Thermal controls 4 components. It's the insulation quantity, it's the quality of the installation, it's thermal bridging, and then the windows. All 4 of those are critical to getting the enclosure right for thermal flow. And finally, vapor flow has 2 key elements. It's the air transport, which is the dominant one, which you already addressed with airflow control above, and vapor diffusion control. And so this is the larger set of best practices. And in bulk moisture, we all know the culprits when it comes to keeping our assemblies from getting wet. It's precipitation, whether it's rain or snow, it's wind-driven rain, it's the gravity or bulk water that falls off our buildings, and then the accumulation of water in the soil, and then below grade, the water that's in the ground. All those water sources have to be managed. And in vapor flow, it's air leakage and it's diffusion. And the reason the arrow for air leakage is so much greater is it is the dominant vapor transport mechanism that is your biggest bang for the buck and most critical to control. More about that in a minute. So when you see these basic diagrams that have been shown for so long, it's all following basic physics. And gravity, we're just draining water from the roof, and we're draining from the walls and opening, and we're draining it from all the components and the openings, and then from the ground, and then from the site and foundation. We're just getting rid of water in a very thoughtful and complete way. And we have all these tools. We have water control layers and flashing and membranes and capillary breaks, and at foundations we have damp and waterproofing, and we have these fabric filters for drain tile, and then just how we grade the site to keep the water running away from the house. So it's basic tools, and we manage the risk with hardly any difficulty. And I like to use this little test to see if people can know how to flash an assembly, and the quiz is flash this correctly. And since we're virtual, I'll show you basically the answer to the quiz. You start at the bottom. And at the bottom, you have your basic first piece of flashing water control. And the most critical thing is it's not flat at the bottom. It has a kind of a kick out because you need a capillary break. If the flashing runs against the surface that you're draining water, capillary action will allow water to kind of wrap under and get the assembly wet. So it's why at the end of every assembly that's being water controlled, bulk moisture water controlled, that little capillary break bend is so critical. Then the next piece going up has to be flashed, and then the next piece going up. And on the back side, you have to start flashing, and the cap, you have a cover with 2 capillary breaks and a slope in the prevailing direction to drain water from the assembly. So hopefully most of you know this is how you would have known how to answer this little test question, how to flash. And when you look at any more detailed diagram of moisture control, all it's doing is what I just showed you on the left. So you see in the case of this roof assembly, you have the kick out flashing. I mean, you have the drip edge flashing at the bottom with the kick out bend so it doesn't have capillary action going underneath. And then you have flashing tape, and then you have the next water control layer of the underlayment, and then you have the kick-out flashing that shingles up one on top of the other, and then finally the roofing covering the whole water control system. So it's just always doing the same basic process, but within the constraints of the assembly that has to be water controlled. And a more detailed kind of run through how this works is the window flashing, which more and more I'm glad to say when I inspect job sites, I'm saying we're getting better and better at understanding this, but it used to be routinely I go out and find all sorts of mistakes flashing windows. But the first thing you do is you have the house wrap goes over the opening, you make this kind of modified eye cut from the top of the opening down, and then about 3/4 down, you go slope cut and a slope cut, and you bend this piece over on the sill. And then you wrap the flaps around the jambs, and then you have a cut at each top so you can have a flap at the top. The next part is you then want to seal along the edges, and only the top three, the sides and the top, not the bottom. And the reason, and then you're going to install the window, but the reason you only do those is so that the water that will get behind the assembly has a way to get out. And 100% of windows leak, all the miter joints, etc. There's always ways for water to get in assemblies. You have to allow a path out. And then with the window installed, you now put the jamb flashings on either side. And then you put the top flashing at the top. And then you kind of put the flap down from the house wrap and tape it. And that's basically just doing the same detail I showed you earlier as a problem in practice. Now, when the house wrap runs to the bottom, it goes over a piece of flashing with a kind of a bent edge for capillary break, and it's always following the same detail I showed you. Now, here's the reality. Probably about 90% of existing homes, 80 or near 90%, don't have window flashing, window pan flashing. As I mentioned, 100% of windows leak, and so we can go take infrared images of older homes, and this isn't that much of an older home, and the evidence that the window draining will show up. You know, there's a classic kind of spreading of the infrared image of the dark color to suggest water. And so this is a high risk for insulating an existing home. Right now, the only way there's no moisture issues is there's enough drying to go through the assembly from inside to out, particularly in cold weather, to dry the wetness that occurs. However, now I insert insulation in the assembly and reduce the drying potential. Now that wetting could create a severe moisture issue, mold, dry rot, whatever it may be. So we have this big, huge issue about how do we retrofit existing homes with wall insulation to meet the latest codes. And then we have the simple details when they're missed are just unnecessary and very expensive. On the left, you see a roof meeting a wall assembly with no drip edge flashing, kick out flashing, and of course the water accumulates at the edges and can damage the cladding or get behind it and damage the wall. And for about a few extra dollars, you can put one more piece of a bent kick out flashing so that you divert the water from collecting at the wall. Very simple details. We mentioned drip edge flashing earlier. That covers the underlayment at the bottom and the sides. When it's missing, again, you can see all the mold and moisture issues that can occur. And here you see then the detail, which is, again, you have a straight piece with a bend to avoid capillary action. And another very critical piece in cladding systems, almost all cladding systems, again, water can get behind them. Turns out one of the cheapest is a little bit better at draining water, vinyl cladding, but you need an air gap to really ensure drainage so water doesn't accumulate behind the cladding where it's pressed against the underlayment. Excuse me, water resistant barrier. On the left, you see wood furring used for the air gap to create an airspace. Much more low-cost approach is these kind of little plastic strips that can do the same job at much lower cost. Only needs a 1/4 inch, 3/8 of an inch, and you're got plenty of air gap to drain the cladding. Finally, vapor flow. I mentioned that air leakage is most critical, and here's why. This is a good study by Joe Stebrick, where Building Science Corporation took a 4x8 sheet of drywall without a hole and with a 1-inch hole, and in a hot, humid climate, measured and calculated the vapor flow through an entire cooling season. And it was 3/4 of a quart of water without a 1-inch hole, and with the 1-inch hole, it was 7 quarts, which was 10 times greater vapor flow due to air leakage. And it gets worse in a cold climate. It was 1/3 of a quart of water versus 30 quarts, this time flowing from inside in the winter out, trying to get out to the cold outside over an entire heating season. So 100 times greater vapor flow due to air leakage. And I remember very early when I first started leading the ENERGYSTAR program, I went out to Minnesota. And everywhere I went, I think it was by code, you had to have all this plastic inside on the framing before you install the drywall. And I was kind of freaking out. I was going, how much risk are you putting on the builder asking them to put plastic behind the drywall? Because plastic's impermeable to vapor flow. So you want to dry both to the inside and the outside, and then you put a dam effectively blocking the vapor flow. It's not like Minnesota doesn't get humid and hot for 3, sometimes 4 months. So you're just creating conditions for problems you don't need. I don't know that the data is there. If you do a good job with the air sealing and insulation, you then also need the plastic. So this is just adding risk when we're trying to solve a problem. It really frustrated me. So then airflow control. Now we manage bulk moisture is pretty much what I said before. It's complete air barriers, air sealing, and flashing the large openings. And there's a long list of air barriers. This is your first and most critical first step you have to take. One of the most important things I did with the ENERGYSTAR program version 2 was I took all the wisdom of all the lessons learned about air barriers from the building science community, and I curated it into a way that it would kind of align with the construction sequencing and organize it so that in the field that it could be managed more easily. That was my biggest effort there. And so we have all these air barriers for walls, shafts, the attic ceiling, and floors. And there's a whole bunch, not enough time to go through them, but if I take just one drop ceiling, it's a good example of just why air barriers are so important. So here's a drop ceiling with a missing air barrier. So in other words, usually the framer comes in and does everything, all the regular structural framing, and even if there's soffits, they'll frame those right away. And that precludes the ability to easily then put an air barrier once this framing is in for the soffit. So often you'll see it missing before ENERGYSTAR made it mandatory in its program. And so when it's missing, basically in a winter condition, as an example, you can have a freezing attic at 20 degrees, the house at 70, and the outdoors would also be about 20. And so fibrous insulation is great at resisting thermal flow, but if the attic's under pressure with almost any amount of wind, you now have pressure that can move the thermal flow through the assembly. So we'll assume that the airspace normally would be 70 degrees since there's hardly any R value in the drywall, but now the pressurized attic will create a convective flow and eventually get a temperature that's a midpoint between the 20 and 70 degrees. In this case, 45. And what's of also concern is that the surface temperatures now get much colder. Anyway, the ceilings drop, as you see in the infrared image on the right, and when you lose control of surface temperatures, you're kind of really make it much, much harder to create comfort. First, surface temperatures have 40% more impact on comfort than ambient air temperature. Excuse me. Got a bug in my throat and I can't get rid of it. Okay, so the next issue is not only have you created all this comfort issue, you have a cold surface right here, and now you have the ability for again, airflow to get there and create moisture on a cold surface. And so all the risks just go up when you leave out one detail, the air barrier. It's absolutely a comprehensive set of air barriers is a must-have. It's very simple. You put that in before you frame the soffit. This is what it looks like when it's done properly. On the left, the OSB sheathing is used and carefully sealed. On the right, you see drywalls used to create the air barrier. And both these examples are like this example with the garage on the right and the soffit up against it. So since the garage is over here, you have to have an air barrier against that wall. It's like an exterior wall. And then air leakage is next. It's 33% of the energy loss in cold climates is attributed to air leakage. That's 3 times greater than the air leakage from either the windows and doors, the ceiling, or the walls. It's a very significant air leakage thermal loss component. And that's why you see such varied ACH 50 targets to manage that energy loss. So you have climate zones 1 through 8, and you have all the program requirements, Zero Ready, ENERGYSTAR, some of the latest IACC requirements in Passive House, and it ranges from 0.6 to 0.15 in zone 8, and you have all the variations for each climate zone, and you can go mad as an industry. And I'm insanely obsessed with simple, and I'm convinced that 1.5 ACH 50 is a great target everywhere. And the reason why 1.5 should be everywhere is because managing thermal losses is not enough. Air leakage contributes to moisture problems. It contributes to air quality issues indoors to the degree that smog gets in, dust gets in, pollen, odors, and also durability issues to the degree that pests get in, and also air quality issues associated with pests. Also, air leakage contributes to greater risk from disasters because the wind can get inside and pressurize a house and cause additional structural damage. When there are wildfires, smoke can get inside the house and really exacerbate health horribly. And also, it's so readily achievable. It's just not that hard to get to 1.5 ACH 50, especially if we use advanced enclosure innovation. And we'll talk more about that a little bit later. And now in air sealing, we have a whole list of air sealing checklists. There are about a half mile of cracks around windows and doors and sill plates. We have penetrations and geometries that have to be managed. I'll take again one example, the drywall at the top plate, again to show you the impact air leakage has. Here, the undulating drywall that's fastened to the top plate on a wall frame adjoining the attic creates pathways because of the undulation for, again, going from more to less, from more heat in the house wants to move up into the attic, and the cold surfaces get created. And again, we mentioned the impact cold surfaces have on comfort. And so there are basic ways that we do this: sill sealer or construction adhesive in new homes. On existing homes where it's missing, spray foam may be your only solution. And then when you look at that whole ceiling interface, beyond just the gap between the drywall and the top plate, it's pretty egregious interface, by far the worst in the house. It's the biggest temperature difference because the summer temperatures can get from 125 to 170, depending where you are in the country. You have a constant stack effect pressure, about 15 CFM up against that surface. You have all these air barrier challenges that, depending on the design, can occur: D-walls and drop and raise ceilings and shafts, and then the wind baffles. And then you have the air sealing with penetrations and ducts and access panels and the aforementioned drywall to top plate and the HVAC losses when systems are in the attic. It's just the interface you have to get right. So last piece about air sealing. And then finally on all this control is thermal, which again is the insulation quantity, the quality of installation, thermal bridging, windows. And where greater accountability situation we're in is because infrared cameras are just like routinely available at very, very affordable costs. They used to cost tens of thousands. For a few $100s, you can put an adapter on your smartphone and get a decent image. and they will reveal all sorts of issues you don't want to have to come back and fix because they're defects when they're found out. And so that's basically just one good reason to really care about thermal flow. So the quantity between the 2015, 2018, and 2021 IECC codes hasn't changed that much. The biggest changes as we go into 2021 is in climate zones 3, 4, and 5, either slab edge insulation wasn't required and now some minimum amounts required, or it's additional foundation slab edge insulation is required, and that's a good thing. The thermal bridging that happens across that slab edge is substantial in cold and hot weather. And then in basement and crawl spaces, there's an encouragement to do continuous insulation besides a typical 15 in the walls or 19 draped insulation. But that's that's just an additional option, so not really an extra requirement. The biggest increase of note would be in the ceilings. The attic insulation is required to be 49 instead of 38 prescriptively, and 60 versus 49. Note, in the 2024 ICC as currently written in draft, it would revert back to 38 and 49. I'll mention 49 isn't that aggressive because if you do a raised hill truss, that drops it to like 40, and if you do insulation on the slope, which we'll talk about unvented attics, that drops it again down to like closer to 30. And same thing with 60 drops to closer to 49 if you're raised hill truss, and then if you on the slope again, it might drop it down to 38 or 40. So even prescriptively, these requirements, when you do normal routine best practices from any high performance program, raised hill trusses, and my personal recommendation of unvented attics, you get much more manageable numbers than the 49 and 60. And lastly, on walls, the biggest thing is just bumping up a little bit more continuous insulation in the colder climates 4 through 8. So that's, so essentially from 2015 to 2021, not very substantial changes, slab edge, attic. And the key thing about installation quality is it kills the R value. So you can have all these prescriptive, meaningful R values, but then if the installation is not right, you can lose up to 70 or more % of that R value. And the key factors we care about are gaps, voids, compression, and misalignment. Misalignment means the insulation's there without an air barrier. Remember, complete air barriers. In absence of an air barrier, any air in this ceiling space can migrate through this fibrous insulation, especially through the cracks and spaces, and get to the outside surface and then look like on the left. So you have in the winter all this heat, potentially vapor transport, creating wetting. It's just a risk you don't need. One common solution is spray foam. We'll talk about another in a moment, just by using advanced wall systems. But it's very simple to use better materials to fix this problem. And again, you want to use closed cell, not open cell, because you want the air barrier. Open cell insulation is open to vapor flow, closed cell is closed to it. I mentioned slab insulation is so important because it's this huge thermal transport pathway for heat to get out in the winter and come in the summer. And there are lots of basic solutions, from continuous insulation that's clad with cementitious board or flashing, or there are even forms where you kind of leave the insulation in place and you don't have to build a form for the foundation. So there's some credits and debits to the insulation cost. And then finally, on thermal control, windows are the R value killer that we can't ignore in cold climates. You see a really good wall, and then these windows are like a funnel for thermal loss in the winter. Let me show you what it looks like by numbers. This is a calculation chart I've run just for 3 wall assemblies. R18 wall 6-inch, R39 wall would be roughly 13-inch, and R60 wall is almost like 20-inch thick wall. And I couple that with ENERGYSTAR 0.3 U-value window and an R7 triple glaze window, or triple glaze window. And I think the assumption here is 15% window to wall area. All these numbers would be worse in terms of the impact windows have reducing a whole wall R value if I use more traditional amounts of window to wall area that builders use, like 20% or higher. So look what happens in an R18 wall with an ENERGYSTAR window. The effective R value for the whole wall drops about 33+%, about 40% to R11. And if I have a triple glaze window, it only drops 20%. And notice that the 13-inch or 39 wall drops 60%. So the more insulation I have in the wall, the more impact on the whole wall R value. And the R60 wall drops to R17, hardly any gain from the R39 wall. So you lose 70% of the rated R value of the insulated assembly. Very significantly, the triple glaze window delivering R14 or almost R15 in a 6-inch wall is almost the same as a 13-inch wall with an ENERGYSTAR window. And it's reasonably close to the R60 wall, that's at R17. So windows are a huge deal in cold climates if you're going to control thermal control. So it leads me to the last section I want to talk about, which is how do we take all this information and get to a better enclosure at lower cost? And essentially, I'm going to suggest moisture control is not perfect enough. This is Joe Steebrook's perfect wall. And when he says it's a perfect wall, he's right for one element, moisture control. For moisture control, you're mitigating the ability for condensation in the cavity, and you're getting also substantial control of thermal bridging. It's a great, perfect wall for moisture control and a little bit of thermal control. And the problem is when it manifests as a actual assembly you have to build, again, one of his sketches, you're going, oh my God, I got a lot of issues here. Productivity, is the labor force able to build this and, without significantly increasing cycle time? Can they build it effectively with the skills they have? The extra quality control risks I have manageable? Is it as good in disaster resistance as other more advanced assemblies that have more impact resistance and wildfire resistance and earthquake resistance? And is it really affordable compared to these other assemblies? And so I'm going to suggest when you go beyond moisture control, maybe this is not perfect enough. And so here are all your wall assembly options for traditional frame walls. You have 2x4, 60 inches on center, which has almost 30% framing factor. You have 2x6, 24 inches on framing on center, which is almost 20% framing factor. You have staggered studs, where you have 2x4 studs with 2x6 top and bottom plates, has a 12% framing factor. And double wall assemblies still have a 10% framing factor. It's because all the framing you need at the top plate, the bottom plate, around windows and doors, you still wind up with significant amount of wood going from inside to outside with thermal bridging. And then you have structural panels, insulated panels that have 5%. I could also make these panels out of concrete. They're precast insulated concrete panels that would have even less thermal bridging. And then I have rigid insulated sheathing with 2% framing factor. So here are all the risks now I believe you have to manage and also reflect in costs, construction costs and ownership costs, moisture, thermal bridging, resilience, quality assurance, productivity, and cycle time. And I'm going to suggest all these traditional options have way too much risk for me. And even the continuous insulation, do I want to manage all those quality and steps and different layers and ask the construction workforce with shrinking skill sets to do that assembly right? And even some of the past projects, we've seen some shrinkage of the continuous insulation that still leaves air gaps. Where I do advanced construction assemblies, again, SIPs, and it can also be SIPs that are concrete and SIPs that just use steel framing. There's ways of doing this so much more effectively with less risk, more productivity, more resilience, same amount of thermal bridging, and even better moisture control. And that's what you have to do is do true cost accounting. So frame wall or SIPs or continuous insulation wall on the right, and you see the thermal bridging reason why we want to do one of these advanced approaches. But comparing the left, again, all those layers I have to manage, all those steps versus just assembling these big, huge panels that are absolutely going faster, less trades, they have less moisture risks. There's no vapor flow path possible through these assemblies where you have the sandwich pressed right against the insulation. And then you have dimensional accuracy, you have advanced hand strength from impact, you have added volume because we'll talk about a 4-inch SIP wall will outperform a 6-inch frame wall. You have all this additional resilience because wildfire smoke can't get in these airtight assemblies, more impact resistance, and less carbon because you're using about 50% less wood than you would in a framed assembly. So you have all the reasons it's better, and just the savings from cycle time, quality risks, and inspections, waste, and rework have to be accounted for, and they're substantial. So here's your SIP option, with just putting in panels, assembling them, and we have these benefits, and let's look how it plays out. Here are all the air barriers I have to manage with typical framing. That's how many go away with SIPs. The only issue would be if I had a whole house fan, I'd have to figure out how to do that. I'd say less than 1/10 of 1% of homes are built with whole house fans. So virtually all the air barriers go away because the SIPs is inherently this massively complete air barrier assembly. The sandwich on the outside, the sandwich on the inside, and then you have these splines for attaching the panels, you have foam between the panels, and then tape, and you have redundant air sealing. It's just so much risk reduction. And then you have all these air sealing requirements for conventional framing. And most of the major ones go away with SIPs. You still have to worry about some sill plates and air sealing windows and doors. There might be some vents, but the most critical, challenging details almost all go away with air sealing. You have to work hard to get a SIP home above 1.0 ACH50. 1.5 is just like a no-brainer, and it's a very conservative level that I use. But virtually all my friends who give me feedback about where their homes are coming out with SIPs, 1.0 is just routinely what they achieve or better. And I mentioned a 6-inch wall outperforms a 4-inch wall. Oak Ridge National Laboratory ran the analysis, and on the left is a 4-inch SIP wall with an effective R14. Here's a 2x6 wall, 24 inches on center with 13.7. So the 4-inch SIPs outperforms a 2x6 wall, and that's with quality installation. And their analysis, when you look at a typical installation, is the 6-inch wall actually performs at R11. And so now you're like almost 20% more thermal control. You have 2 additional inches of volume around of space around the entire footprint for all the additional volume in the home. So look at all the cost savings I have from framing and installing insulation and air sealing and all the extra costs. The grade 1 insulation might be $1,000 to $1,500 of saving. All the air sealing and air barriers are $1,000, $2,000 savings. I assume $1,000 to $1,500 for rework, reduce waste, and containers that you have to get rid of, $1,000 to $2,000, and 5 days of time is about $2,500 to $4,000 of cost savings. Plus, I have 30 square feet additional square footage in about a 1,500 square foot home. And again, $200 a square foot. That's about $10,000 to $15,000 of savings of additional value. All the resilience, impact, wildfire smoke, et cetera, I'll just estimate it $2,000 to $4,000, and all the quality savings and rework and waste $2,000 to $4,000. This is just real numbers that are not counted and hidden when we compare a SIP package to a framing package, and we have to get to lower true cost. Then the benefit of a vented attic is substantially significant. Here's a house with a vented attic, and we're missing the top side air barrier at the attic insulation, which is why the codes require so much more insulation in the attic than the wall. And so we have all this insulation, about almost 50% air barrier missing, at the most egregious interface we talked about, the ceiling and the attic interface. And then we'll put the heating and cooling up there and have all these egregious losses on the performance of that system. So an unvented attic, in contrast, reduces cycle time because there's so many less construction points that have to be done. It's better, you have more conditioned space, all that extra volume that you're adding that's effectively ready for conditioning. It's more efficient, more comfortable, much greater strength. Without the vents in the attic, you don't have the wind able to enter through those vents, pressurize the attic and cause structural damage, introduce smoke, introduce moisture. It's stronger impact resistance and more fire resistant because wildfire and bruise can't get into the assemblies. And the cost savings we mentioned are from all the things you don't have to, that come along with the SIPs. You don't have to do the insulation, the air sealing, et cetera. You don't have to do the vents. You don't have to do the air barriers and sealing, and all the time you save. And so you can just see the difference between the attic insulation that's just blown in versus having a complete 6-sided assembly installed with a unvented attic. And then you have all the additional volume, and you have spaces for MEP, mechanical, electrical, plumbing, and then you have all this extra resilience, wildfires, impacts, wind, snow, and cycle time is always undervalued. First are the cost savings from just all the carrying costs of owning a business and having a home take 2 or 3 months longer to build, or 4 weeks longer to build. And you have the extra insurance, all your overhead costs, or your extra mortgage you're spending for your construction loans. Every time you extend time, there are just huge cost impacts on your business. And then time also affects profitability. The most significant factor is, again, velocity. If I'm building with 1 month or 2 months shorter cycle time, I might be building another 10, 20, 30 homes a year, times $30,000, $40,000 of margin for each of those homes, and it's quickly another $500,000 of revenue I gained because I have greater velocity, and I can price more competitively and better cash flow, and much less risk because I'm not getting maybe into a cycle where interest goes up or the other market factors that constrain my ability to sell the home. So cycle time is just a huge cost. And the fact that these advanced systems built solutions reduce cycle time is so undervalued and underassessed when people pick a wall assembly. And I'll finally put it all together by showing what happens when you integrate the entire advanced systems built solution into the design. There are a lot of things you have to do to optimize for SIPs. If I do that, I can take this frame home, for instance, and convert it into a home without a basement with a shallow frost protected footing, and basically trade off the very expensive to build basement for a much cheaper ability to use the volume created by the SIP attic. And that's a huge cost savings. So I'm saving up to $6,000 on the shallow frost protected foundation. I have all the wall framing that's free on the gable ends that's there to be used. I don't have to put egress windows in that are expensive and build those openings and escape hatches. I don't have air sealing and barriers at the attic interface, venting, waste, time, and a second floor space might be worth $100 extra square foot to below grade space. So the trade-off may be worth $80,000 to $100,000 more. So this is when you start getting to really significant cost advantage, savings, and added value. And the whole performance approach we're taking with Housing 2.0, the big message I want to get across is there are all these benefits. We're lowering costs of the construction from the enclosure, from mechanical, electrical, plumbing. We're lowering the cost of ownership for utilities, maintenance, health, water, insurance, and all that revenue from solar when we add it. We're enhancing wellness for healthier living and better protection, and we're adding all this value, smart homes and disaster ready and electric ready. And when we go to market, it's like the answer is zero, and that is the wrong answer. You have to integrate, account for all these hidden savings and values, the cost advantage of high performance. And you realize these are serious numbers, tens of thousands of dollars of value. I've shown you just in the enclosure how I get to easily tens of thousands of dollars. The same with comfort systems, talk about next week. Then just the utility savings and maintenance savings, and just what is health worth, and all the health expenses you can avoid, and then all the future value of having a home that will stand the test of time. Easily $150,000 to $200,000 of cost advantage for this high performance home. So my last recommendations before handing off to Ken is get on the path to zero. You have all these certification programs. Everyone should be doing that. Customize your performance optimization framework. Housing 2.0 lays out about 50 best practices. You don't have to do them all. Figure out what's best for your market, your customers, your tolerance for change, whatever it may be, and figure out a framework for you. And commit to moving forward and keep incrementing improvements. And you have to have a home performance expert, either in-house or on retainer, to help advise almost all your product and assembly decisions. And most importantly, you have to optimize true cost. If you're ignoring all the hidden costs we talk about, you just get to the wrong answer. So I hope some of this makes sense. And now, Mike, I'm going to hand off to Ken.
Very good, sir.
Thank you,
I'm going to
Sam.
hand it to Ken. And you should have the option to share your screen now.
Thank you, Sam. So I'm going to be brief, but we do want to talk about how to ventilate when we, and I'm with you, Sam. I think 1.5 CFM is spot on. Hold on, did my screen disappear?
Nope, it's looking good. Ken, I can see it. Oh, now I can't see it.
I'm so
Hold on,
sorry,
it's coming
guys.
back.
My screen disappeared. Here we go.
Now it's
Should
looking
be
good.
back now.
Yep, I see your first slide.
As you know about Panasonic, I have a fan for every day of the month. I have exhaust fans in the bathrooms. I have ERVs, supply fans, dryer fans. I have all sorts of fans. But today I wanted to talk about ERVs because when we get to that 1.5 air changes per hour, it's super, super critical that you have a mechanical ventilation system that's in place and that it both works and it should be invisible to the occupants, because if the occupants can hear it, they will shut it off. And that's one of the biggest challenges we have with all ventilation strategies is the occupants sometimes don't understand the value of having ventilation in the house. So I want to talk about ERVs and real quick, because the challenge for most builders is that they can't explain necessarily how the ERV works. The ERV, as you all know, moves an airstream, a supply airstream. It has an exhaust airstream, and it pulls humidity, it pulls moisture and temperature from one airstream and puts that into the other airstream. And it doesn't really matter. And what the ERV ultimately wants to do is create balance, right? So I've got this slide, and this is probably premature here, but I want to talk about if I have 70 degrees at 50% humidity inside my house, that airstream contains about 54 grains of water. If it's cold outside at 50 degrees at 80% humidity, that airstream contains approximately 42 grains of water. But there's a difference in the vapor pressure because of the temperature, right? So as those two airstreams pass, the ERV simply wants to help those two vapor pressures become one. So if you look at the vapor pressure, the average vapor pressure is going to be the average grains is going to be around 48 grains of water. It's going to try to move everything into that middle area. So what that'll do for you is it literally helps to resolve some of that vapor drive. More importantly, though, it keeps the house at a really consistent humidity level. It keeps the occupants with a really consistent breathing level. Because it's supply air also, it allows us to filter that inbound air so that I can manage any of the particulates, the VOCs that come from outside, which would be your PM 2.5, which would be your pollens, which would be to some degree your wildfire smoke. And then it also helps to diffuse and remove some of the VOCs we create on the inside, which again is that PM 2.5, the viruses, the bacteria that we as humans outgas, and of course the water vapor that we outgas. All of this, the ERV uses basic science to manage that function, right? High pressure, we know high pressure moves to low. We just demonstrated that with water vapor moving across. Wet moves to dry. It wants to go to that dry space. So, and hot moves to cold. So it's going to tend to warm up that cold air as it comes in. And what we do with the ERV is and this is not just Panasonic, this is all ERVs in particular. It allows these natural physics to work to manage our comfort. It also diminishes the cost to our mechanical systems. And the beauty of the ERV is that it really only takes about 50 watts of energy to bring all that in and out. I will tell you that from an ERV perspective, we have to remind ourselves that the ERV is neither a heater nor is it a cooler, in the sense that it's neither a heat source or air conditioning source. But it will always take the edge off of whatever airstream is coming through. So as you move along, one of the things that I remind everybody, if you need help with your ventilation strategies, there's no reason that the ventilation strategy should add an excessive amount of cost into your build. What it does is, as Sam talked about earlier, it'll help with that resiliency over time. It keeps that moisture load from creating that vapor drive from inside to outside, and it'll help balance that pressure from outside to inside, so we don't have a higher vapor drive from outside to inside. So part of managing that envelope, if you will, that high-performing envelope, is taking away some of those external and internal pressures that drive water vapor. So if there's ways that we can help you, and I have solutions for every application, I promise, but it really does start with the ERV. So if I can help you, or Panasonic can help you in any sort of way, just let us know. Sam, thank you for the time. I really do appreciate it. And I'm going to turn it back over to Sam and let him close us out.
Well, Ken, hold on. Don't run away yet, because I want to make sure that who has questions for you is able to ask you, because if nobody else does, I know I actually have one. First of all, I want to make sure to just point out to our audience that I really do appreciate Ken being able to not just talk about Panasonic, but talk about the industry in a very general way. That's really helpful. And I have a general question for you. As we head into cold and flu season, I'm aware of some of the filtration options for bettering indoor air quality, HEPA filters and UV, but what other filtration options are there out there?
So keep in mind when you do filtration, right? What air are we filtering? If we're filtering the outside air coming in, I'm not so worried about cold and flus coming from the outside in. Okay. I might worry about pollen or something like that that's going to be a big asthma trigger. My cold and flu issues will always come from the inside. It's cold and flus come from humans, right? So in that case, we don't necessarily want to filter that. We want to exhaust that as quickly as possible. So that's part of what the ERV and the exhaust fans that you have in your house can do, is they take those particulates, those bacterial or viral particulates, and get them out of the house. So there's two things we look at, right? Is this product, or is this virus, is it ballistic or is it buoyant? And one of the things that can occur with high moisture loads inside the house is it will hold these viruses buoyant. If something is ballistic, it's falling to the floor, it requires touch, contact, hand to mouth, or whatever to get into your body. However, if it's buoyant, if it's floating in the air and I'm breathing it, that's a bigger challenge, right? So we want to get it out of the air. We want to dilute it, diffuse it, evacuate it. Is that helpful? I run into that a lot, where people think, oh, I'm going to put a filter in the house. And I'm okay with that, by the way. You can put filters in your house and recirculate that air. Your furnace filter may have a recirculation capability, and that's great. But the reality is, you have to run that to make it work. So if it's not running, it's not working.
Yeah, no, I really do appreciate it, Ken, because and I appreciate the delineation between the two, right? Buoyant, ballistic, and influx and recircuits. It's just really helpful because I have a feeling a lot of people right now are thinking about, oh gosh, cold and flu, and Panasonic is known for its indoor air quality, excellent products, and it's like, okay, I think people look to you for a lot of answers, and so I appreciate the depth of the answer as well. I appreciate it, really do.
Yes, I have a ton of media stuff, magazine stuff coming out probably in the next 6 weeks. They're going to see a ton of different articles I've been doing with different writers on cold and flu season and viruses and bacteria and how to get it out of your house. Because, and I'm here to tell you that we do want to create a great envelope. But then once that envelope's created, we have to move that air in and out in an intelligent way. And it can be done really inexpensively.
Well, let's stick with you for just a second, Ken. So our friend Zoran had a question about ERVs. Should they be fully ducted, or what does a partially ducted or a hybrid ERV even mean?
So partially ducted or hybrid, oftentimes they'll take that supply air and use the ducting from your furnace system as that pathway to the rooms. So that, and I can't speak exactly what he's referring to, but that's one of the hybrid solutions, where the other is we'll run both the exhaust and the supply into that cold air return of the heating fan. Oftentimes I'll see it where we only want to run, I don't want to say only, we'll see supply air run to the bedrooms, right? We want to pressurize the bedrooms so that the air moves from that high pressure space in the bedroom out into the hallway common space, and then it's evacuated out. So I can minimize the cost of the installation by having maybe air supply into each of the bedrooms and then having the exhaust from a central location. So all of that becomes, you see a lot of guys will want to go, manufacturers, I will say they'll want to go at a supply and an exhaust in that same room. I'm not always a big supporter of that, only because, again, I have to get, if I raise the cost of the house so much that the builder can't sell it, I've really failed both of us. So the reality is air is going to move from high pressure to low, no matter what. So if I pressurize that bedroom, I move it out. And then also I don't worry about air from, say, a great room coming in where you might have pets or whatever. If somebody's allergic to animals, I can keep them out of that room, and I can drive air into that room, and that air moves out, so it never basically contaminates from room to room, but it moves to that central space and it's evacuated away.
Okay, and then going back to his first question, ERVs be fully ducted?
Does it have to be fully ducted? I'm sorry, I might have missed the question.
No, it's okay. He was just asking if ERVs, should they be fully ducted?
It's not necessary. I don't think it's necessary. What is necessary is the ERV has to run continuous. So if you're going to run it through an air handler, do you want the air handler to run continuously, or can it run past the air handler cleanly? And that's a question for your HVAC professional on the setup of your individual location. Certainly the best, most efficient way for the ERV is to be independently ducted. However, I'm not always, I think you have to use some of the stuff that you have at hand. I don't want to have 14 different ducts running to a room when I can use a central duct basically from the HVAC system.
Ken, if I could contribute to this, what happens as we use better and better enclosures, the subject of the discussion today, the loads get so small that the difference between the size of the duct for ventilation and for heating cooling supply gets closer and closer to the point where the benefit from having separate ducts for ventilation are quite a bit diminished. So the benefit of a high performance enclosure is you can use probably the same ducts with a lot more assurance you'll get enough mixing and air movement to all the rooms.
No, that's exactly right. Once you get the high performance enclosure, you can do so much more with the ventilation. You have better results with the ventilation. You can, depending on the cubic space of the area that you're trying to ventilate, you can speed fans up without even knowing it. You can slow it down without having it negatively affect the dilution component. If it's in a smaller space, it really starts with the envelope, as you talked about today, Sam. But I'll tell you that, every bit of ventilation you can get, and I do like a balanced ventilation strategy because I both dilute and evacuate at the same time. It's for us as humans, it's really is a changing of the health structure of the people, of the occupants in the house.
Yeah. Well, Ken, thank you so much for all this, and I'm leaving your contact information up there for a couple more seconds so that people can get that. Ken is a wealth of knowledge, and we really thank him for joining us today. And I'm going to kick it back over to Sam here, because we do have some other questions that aren't specific to Ken, but Ken, you're certainly welcome to hang here with us because you may have.
I'm here for the duration.
Fantastic, awesome. So we had a question from Bill on the SIP roofs. You were talking about SIP roofs earlier and SIP attics and that sort of thing. Do you need to reinforce the roof trusses due to any additional weight?
What a great question, and a very important question. If you do it right, there shouldn't be any trusses. And the reason why SIP costs have sometimes just create so much sticker shock is because you have these redundant systems. The panels are structural, but you still have the trusses as well. So ideally, if you design for the panels and the spans of the panels, you can locate columns and ridge beams so that you have no need for the trusses. So the concept is no trusses. If you're doing trusses as well as SIPs, you're incurring a lot of extra cost, and the benefit may or may not still be cost effective, but when you get rid of the extra trusses, it almost surely is.
All right. Got a question from Tiffany. She was wanting to know if you could speak to the value of sustainable materials in choices. Her comment was, foam in any form is still primarily a petroleum-based product with no circular option and great waste in installation.
Everyone has to figure out a balance between embodied energy and operational energy, and find something that works for them. If they think that they want to set a path for how you do virtually no embodied energy and petroleum products and so forth, that's great if you can sell it. What I find is that in the right applications and very limited applications, I'm not worried. If my home's going to last 200 years and I got foam between two sandwich panels in that SIP assembly, there's so many other factors contributing to climate issues. A 200-year use of that product or 150-year use of the product is palatable to me. So, but everyone will draw their line where they want to. And I think same thing with foam in the band joists. It's just such the perfect material for the project. It lets me, even sometimes using SIPs, the framing will go on top of the SIP wall rather than be hung on hangers off the wall. And so you do have to still manage the band joist, and I would say use the foam. But again, I'm not saying you're wrong not to. You just have to be able to sell all the extra costs it takes to do it. And so I don't want perfection to be the enemy of the good. If I'm getting a house down to zero energy, if I've reduced the wood 50% or 60% because I use this advanced wall system, if I've used a precast concrete foundation that uses 70% less concrete, I'm good. Those are the egregious materials and factors, and I think we effectively manage them. But I don't want anyone to feel bad because you're committed to a much higher level. Just make sure you're able to sell it, translate the value, and I root for your success.
Final call for questions from our group. I do have another one here from our friend Zoran. He was curious how the HERS program, how does that relate or interact or influence either the Zero Energy Home or the Zero Energy Ready Home programs?
The HERS program is just so important. It serves as the metric for consistent enforcement of a set of program requirements. So that's where I see it has tremendous value. And most importantly, it creates an infrastructure of verification professionals who can provide all this value to the industry. You know, the building departments really can do drive-by inspections, and you have this HERS rating verification infrastructure. It goes and adds all this extra quality control that once it's there becomes systematically integrated into the builder or trades best practices because they know they're being, the oversights there. So the HERS metric's invaluable, but what I caution people to make sure they understand is not using the savings numbers as they're reported, because the HERS energy savings, utility bill savings, are benchmarked to the 2006 IECC. And again, there's a 30–40% improvement from 2000 IECC in all the latest codes, sometimes 50%. And so those savings would be way overstated. And I get concerned about promising a certain amount of energy savings. The benefit of these homes is health. It is the energy savings are enough to warrant the investment in the better performance. It's the, it's just the, everything about the durability, the quality construction. There's so many reasons people want high performance homes. So you don't need to overstate the energy savings. So, and that's because the HERS metric, it's tough because you can't keep changing the benchmark, and then the old scores become uncomparable to the new scores. It's not their fault, but you have to know not to use those numbers. So that'd be my only caution. But HERS is critical for ensuring you can do these programs, and out in the field, there's a measurement system that gets you the results that are specified.
And let's expand on that for just a second, Sam. You're right, you can't really change the benchmark. So the question is then, you just keep lowering the number that you're asked to hit or required to hit for an incentive or a code then?
That's right. So where the HERS index benchmark for ENERGYSTAR used to be 75 and it dropped to 70, now it might be 65. It just keeps dropping, and the rigor of the program ramps up. Same Zero Energy Ready, the benchmark used to be 55 and it's now high 40s, and it's just all these programs have a consistent benchmark. And like I said, that would change instantly if you peg the HERS score to a higher code than 2006.
So then here's the fun question that came in from Zoran as a follow-up. Does a Zero Energy Home through the Zero Energy Home program get a HERS of 0?
Yes. Well, the HERS index is able to incorporate the solar energy system if it's there. And HERS, I think the HERS index considers anything with a score of 10 or lower, 0 or negative numbers, as zero energy. So yes, you can get to a 0 because the HERS index is inclusive of the solar system. Note that the HERS index requirement for the ENERGYSTAR and Zero Ready program are without the solar system. So it's a rating without the solar system. You can't use solar to offset other high-performance home improvements targeted by the program.
I lost my connection for just a second. Now I'm back.
You're back.
Sorry about that. So then on the zero energy ready homes, what kind of range do those typically fall in?
They're going to generally be, I'll estimate roughly in the 40 to 48 range, maybe 50 on the HERS index.
Okay, all right.
The colder you get, the lower the index in terms of in other words, the higher the climate zone number, the lower the HERS index threshold becomes, or the rigor of it gets higher.
Okay. All right. Well, that concludes our first seminar, but we're only 25% of the way done. Our next seminar is going to take place next Thursday, October 24th, at the same start time of 12 p.m. Eastern. As Sam mentioned earlier, we are going to be discussing comfort, and Sam will get a kick out of this. It will fit with the observation of the day, but you'll want to tune in to find out what that is. Thank you so much for
Halloween.
Nope, not Halloween. That's 2 weeks from now. That's 2 weeks from now. Thank you so much, though, for attending today. Thank you to Ken Nelson very much for his wonderful insight and for Panasonic's sponsorship, as well as Schneider Electric, Jinko Solar, and LG HVAC. We very much appreciate our sponsors. Until next time, stay safe, stay healthy, and take care, everyone. So long.
Hey, thank you.